Hi everyone, in this video we are going to talk about introduction to proofs. First we are going to give a brief introduction, then we are going to study some of the methods that are available for proving theorems. We are also going to see some mistakes that we can make in proofs, and finally we are going to state the conclusions. A proof is a valid argument that establishes the truth of a mathematical statement. Notice that from previous videos, we already know what is a valid argument. We also know what is the truth value of the mathematical statement. If you didn't watch those videos, I'm going to leave the link below, so please watch them before you move forward with this topic. A proof can use the hypothesis of a theorem, if there is any. It can also use axioms assumed to be true and previously proven theorems. Using these ingredients and rules of inference, the final step of the proof establishes the truth of the statement being proved. We are now moving from formal proofs of theorems toward more informal proofs. As in the previous videos, we saw that in each proof we need to show every single step, and we need to justify every step with the rules that we are using. So in this case, now we are going to move towards more informal proofs, and you will see what is the meaning of that during this video. So formal proofs of useful theorems can be extremely long and hard to follow. In practice, these proofs are almost always informal proofs. In these informal proofs, sometimes more than one rule of inference is used in each step. Some steps may be skipped, the axioms being assumed and the rules of inference used are not explicitly stated. This doesn't mean that you can do it in any way you want. For instance, if you skip one step, that step must be obvious for the reader. Informal proofs can often explain to humans why theorems are true, while computers are perfectly happy producing formal proofs using automated reasoning systems. Obviously, the computer cannot make an informal proof. Proof methods are important because of the applications. They can be used to verify that a computer program is correct, to establish that an operating system is secure, to make inferences in artificial intelligence, to show that system specifications are consistent, and many others. Therefore, understanding the techniques used in proofs is essential both in mathematics and in computer science. So now we start with some terminology. Formally, a theorem is a statement that can be shown to be true. The term theorem is usually reserved for a statement that is considered to be somewhat important. Less important theorems sometimes are called propositions or lemmas. Theorems can also be referred as facts or results. Remember that I mentioned in previous videos how important are definitions in mathematics. If you see from the definition of a theorem, it is a statement that can be shown to be true. What does it mean? It means that if it is not true, then it's not a theorem. Here we cannot apply the same than propositions. Okay, remember, propositions are statements that can be true or false. In the case of a theorem, it has to be true. It cannot be false. A theorem may be the universal quantification of a conditional statement. These statements can have one premise or more, and it always has a conclusion. However, it may be some other type of logical statements. The way that we demonstrate that the theorem is true is with a proof. Remember, we already saw how to create formal proofs in this case we are going to move toward a more informal proofs. It doesn't mean it is just an informal proof. Is, as I explained before, there is some rules. Okay, the reader need to find it obvious the steps that are being skipped and so on. A theorem may be the universal quantification of a conditional statement with one or more premises and a conclusion, as I mentioned before. So let's see this example of a theorem. The unique factorization theorem states that every integer greater than 1 either is a prime number itself or can be represented as a product of prime numbers, and that moreover, this representation is unique up to or except for the order of the factors. What do we have here? We have here several premises and we have a conclusion. What is the conclusion in our case? The conclusion is that the number, it is prime number itself, or it can be represented as a product of prime numbers. Okay? And then the premises in our case is that the number is integer and is greater than 1. So in this case we have two premises. This is an example of a common theorem. Through this video series you will see more of them. A proof is a valid argument that establishes the truth of a theorem. We already know what is a valid argument, and in previous videos we made some proofs. So the statements used in a proof can include axioms, which are statements we assume to be true and we don't need to prove them, the premises, if there are premises, and previously proven theorems. Axioms may be stated using primitive terms that do not require definition, but all other terms that we are going to use in a theorem and the proofs must be defined. Rules of inference, together with definitions of terms, are used to draw conclusions from other assertions, tying together the steps of a proof. In practice, the final step of a proof is usually just a conclusion of the theorem. However, every time we create a proof of a theorem, as the last step, we are going to recap the statement of the theorem. So we make more clear the point that we want to prove. A less important theorem that is helpful in the proof of other results is called a lemma. Usually complicated proofs get easier to understand when they are proved using a series of lemmas, where each lemma is proved individually. This technique is a similar technique used in algorithm design that is called divide and conquer. So in this case, we are just trying to divide the big theorem, the big complex theorem, in smaller parts that we can prove those smaller parts individually. After we prove the individual parts, we use those partial results to prove the theorem. That makes our proof more understandable and easier to read for everyone. A corollary is a theorem that can be established directly from a theorem that has been proved. Sometimes you prove a theorem that generalizes a certain conclusion, but it can be useful to have a theorem for a specific case of the general theorem. That can be written as a corollary, and because it is a specific or special case of a theorem that has already been proven, it doesn't need a proof. A conjecture is a statement that is being proposed to be a true statement, usually on the basis of some partial evidence, a heuristic argument, or the intuition of an expert, but is still not being proved. When a proof of a conjecture is found, the conjecture becomes a theorem. Many times conjectures are shown to be false, so they are not theorem. So remember, this is a very important point. Theorems are always true. They are not like a proposition that can be either true or false. I'll repeat it again just to make sure you don't forget. A theorem must always be true, otherwise it is not a theorem. Before we introduce methods for proving theorems, we need to understand how mathematical theorems are stated. Many theorems assert that a property holds for all elements in a domain, such as the integers or the real numbers. Although the precise statement of such theorems needs to include a universal quantifier, the standard convention in mathematics is to omit it. Then let's see an example. For example, the statement if x greater than y, where x and y are positive real numbers, then x squared is greater than y squared, really means for all positive real numbers x and y, if x is greater than y, then x squared is greater than y squared. It is important to get this right. You will see this type of statements in many places and you need to understand the real meaning. Again, notice that in the first statement, we didn't use the universal quantifier. However, in that case, the universal quantifier is implicit. We assume that the reader will know that the meaning of the statement is that it's valid for all positive real numbers. To prove this type of theorem, we usually follow 3 steps. We select a general element of the domain. Then, we show that this element has the property in question. After that, universal generalization implies that the theorem holds for all members of the domain. These are the 3 common steps that we follow every time we want to prove the previous type of theorem. So, proving mathematical theorems can be sometimes difficult. Therefore, we have to use all available ammunition that we can have. And we also need a powerful battery of different proof methods. These methods will provide the overall approach and strategy of proofs. Understanding these methods is a key component of learning how to read and construct mathematical proofs. And yes, you need to learn how to read proofs and also how to create them. When you construct your own proofs, be careful not to use anything but axioms, definitions, and previously proved results as facts. Remember, everything you are going to use, it must be proved. Otherwise, you will be making mistakes while proving your theorem. Therefore, what you prove won't be valid. So, in this case, we need to show that the conditional statement is true. As you can see, the theorem has the form for all x, p at x implies q at x. So it is a conditional statement. And we want to prove that this conditional statement is true. Because of this, we now focus on methods that show that conditional statements are true. Our goal is to show that P at C implies Q at C is true, where C is an arbitrary element of the domain. Remember, this is the first step. We choose an arbitrary element of the domain and we prove that the condition holds for that specific element. When we prove that, then we apply universal generalization. Recall that P implies Q is true unless P is true but Q is false. Remember that? We see that when we studied the truth table for the conditional statement. If you don't remember that, you can go back to the video of truth table. I'm going to leave the link below in the description. Note that to prove the statement P implies Q, we need only to show that Q is true if P is true. Now, we will see the most common techniques for proving conditional statements. After that, we will discuss methods for proving other types of statements. Remember, if you don't understand why to prove that P implies Q is true, we need only to show that Q is true if P is true, please go back and see the truth table for the conditional statement. Then you will realize that when Q is true if P is true is all we need to prove. When you read proofs, you will often find the words obviously or clearly. These words indicate that steps have been omitted, that the author expects the reader to be able to fill in. Unfortunately, you must be very careful here because this assumption is often not guaranteed, and readers are not all sure how to fill in the gaps. Be especially careful if you are a student writing a test. In this case, you must make sure that the lecturer can fill in the gaps so you will get good marks on your solution. I always recommend the students not to skip any step, especially when they are being assessed, just to avoid unnecessary problems while the lecturer is marking the solutions. So, we should try to avoid using these words and try not to omit too many steps. We just want to avoid problems. However, if we include all the steps in certain proofs, our proofs will be often excruciatingly long and difficult to understand. So the key point here is to use the right balance in the right places. Let's see our first method to create a proof, which is direct proofs. A direct proof of a conditional statement P implies Q is constructed when the first step is the assumption that P is true. Subsequent steps are constructed using rules of inference, with the final step showing that Q must also be true. Remember that to create proofs, we usually have to make some assumptions. You already saw that type of proof when studied rules of inference. If you are not comfortable with rules of inference, I recommend you to watch the videos on the description that explain that specific topic. Do not go deeper in proofs without mastering rules of inference. A direct proof also shows that the combination P true and Q false never occurs. Why? As I told you before, if you have any doubt on why these type of things can happen or are in that way, just please go and check the truth table for the conditional statement. You will see that P true and Q false give us as a result that P implies Q is false. And because the theorem has been always true, then that is what we have to show is that that combination never occurs. So we assume that P is true and then we use axioms, definitions, previously proven theorems, rules of inference, and then we show that Q must also be true. If we do that, then we prove our theorem. Direct proofs of many results are quite straightforward, with a fairly obvious sequence of steps leading from the hypothesis to the conclusion. However, direct proofs sometimes require particular insights and can be quite tricky, as you will see in some of the examples. Let's see the following example. The integer n is even if there exists an integer k such that n is equal to 2 times k. And n is odd if there exists an integer k such that n is equal to 2 times k plus 1. Two integers have the same parity when both are even or both are odd. They have opposite parity when one is even and the other is odd. This is our definition, and then we are going to state the theorem. So give a direct proof of the theorem. If n is an odd integer, then n squared is also odd. So now we have to prove that this theorem is true. Note that this theorem states that for all n, p and n implies q at n, where p at n is an odd integer and q at n is n squared is odd. So we start here assuming that the hypothesis of this conditional statement is true, which is p at n. So p at n is true, therefore n is odd. By the definition of an odd integer, it follows that n is equal to 2k plus 1, where k is some integer. We want to show that n squared is also odd. So we have our first equation. Because n is odd, then there exists a certain k such that n equals to 2 times k plus 1. If we square both sides of this equation, we get n squared equal to 2 times k plus 1 squared. Okay, now we can say that the right side of the equation is 4k squared plus 4k plus 1. This is basic algebra. We just need to develop that right side of the equation. Now, if we choose a common factor between the first two terms as 2, this will give us a result that 4k squared plus 4k plus 1 is also equal to 2 times 2k squared plus 2k plus 1. Now, by definition of an odd integer, we can conclude that n squared is also an odd integer. As you can see, n squared is equal to 2 times a certain integer plus 1, which is the definition that we saw at the beginning of this exercise. So, consequently, we have proved that if n is an odd integer, then n squared is also an odd integer. Notice that here we are doing a recap of a theorem as the last step. That's what you should always do. The last step of the proof must be a recap of the theorem. So you make your point very straight. Let's see another example. Give a direct proof that if m and n are both perfect squares, then n times m is also a perfect square. An integer a is a perfect square if there is an integer b such that a equal to b squared. As you see in this example and from the previous one, we always have to state the definitions, so we know what exactly is what we have to prove. Again, to produce a direct proof of this theorem, we are going to use the 3 steps we mentioned before. We are going to assume that the hypothesis is true, then m and n are both perfect squares. By definition of a perfect square, it follows that there are integers s and t such that m is equal to s squared and n is equal to t squared. That's why it is important to have our definitions in place, because we usually have to use them to make the proof of a theorem. The goal of the proof is to show that m times n must also be a perfect square when m and n are. So let's see our solution. M is equal to S squared, N equal to T squared. Remember, we are doing that because we are assuming that the hypothesis or the premise of the theorem is true. So now, if we multiply M times N, we get S squared times T squared. So we now develop the right side of that equation. S squared times T squared is the same or is equal to S times S times T. We can also say that S times T is equal to S times T times S times T. Here we are using the commutative and associativity of the multiplication. Okay, remember, 2 times 3 times 4 is the same that 2 times 4 times 3. Okay, those are rules that we don't need to explain, we don't need to prove them. Those can be used as axioms because those are results that are already being proved. So if we have now S times T times S times T, that is equal to S times T squared. Okay, then we have that M times N is equal to the square of a certain number. So by definition of a perfect square, it follows that M times N is also a perfect square. Okay, because it is the square of S times T, which is an integer. We have proved that if M and N are both perfect squares, then M times N is also a perfect square. As you can see here again, we are doing a recap of the theorem just to make sure that our point is very straight. As we saw in the previous examples, direct proofs lead from the premises of a theorem to the conclusion. They begin with the premises, continue with a sequence of deductions or logical steps, and end with the conclusion. However, we will see that attempts at direct proofs often reach dead ends. So what can we do in that case? So in that case, we have to use another strategy. Proof of theorems that are not direct proofs, that is, that do not start with the premises and end with the conclusion, are called indirect proofs. We are going to see now examples of this type of proof. An extremely useful type of indirect proof is known as proof by contraposition. So remember that when we studied logical equivalences, we saw that the contrapositive of the conditional statement is logically equivalent to the conditional statement. In another way, the conditional statement P implies Q is logically equivalent to its contrapositive no Q implies no P. Therefore, the conditional statement P implies Q can be proved by showing that its contrapositive no Q implies no P is true. In a proof by contraposition of P implies Q, we take no Q as a premise, and then we use axioms, definitions, and previously proven theorems together with rules of inference, and we show that no P must follow. In another way, we first transform our theorem using the contrapositive, and then we just make a direct proof. Let's see the following example. Prove that if n is an integer and 3 times n plus 2 is odd, then n is also odd. We first attempt a direct proof. We assume that 3n plus 2 is an odd integer. This means that 3n plus 2 is equal to 2k plus 1 for some integer k. Now we can see that 3n times 1 is equal to 2k, but there doesn't seem to be any direct way to conclude that n is odd. Because our attempt at a direct proof failed, we next tried a proof by contraposition. So this is our theorem. If 3n plus 2 is odd, then n is odd. Now the contrapositive will be not n is odd, then not 3n plus 2 is odd. We can write this in a better way. We just say n is even, then 3n plus 2 is also even. This is the contrapositive of our theorem. Now let's try to prove the contrapositive. Okay, by definition of an even integer, n is equal to 2k for some integer k. So if we substitute 2k for n, we are going to get this equation. If you see 3n plus 2, we substitute n by 2k, we get 3 times 2k plus 2. That is also equal to 6k plus 2. And if we extract 2 as the common factor between the two terms, we are going to get 2 times 3k plus 1. Okay, so now this tells us that 3n plus 2 is even because it's 2 times some integer, and therefore is not odd. This is the negation of the premise of the theorem, because the negation of the conclusion of the conditional statement implies the hypothesis is false. In other way, not Q implies not P, then the original conditional statement P implies Q is true. We just prove that the theorem, if 3n plus 2 is odd, then n is odd. As you see here again, we are doing a recap of the theorem to state that we finished the proof. So there is another type of proof that is called vacuous and trivial proofs. So for we to understand this type of proof, let's use the truth table of the conditional statement, the one that I mentioned before in several times. As you can see, every time that P is false, then P implies Q is true. Can you see that? We have two rows that P is true, and we have two rows that P is false. In the two rows that P is false, it doesn't matter what the value of Q is, the conditional is always true. Consequently, if we can show that P is false, then we have a proof. Okay, we just proved that the conditional will be true. This type of proof is called a vacuous proof. On the conditional statement, P implies Q. So this type of proof is often used to establish special cases of theorems that state that the conditional statement is true for all positive integers, for instance. We also have another type of proof that is called proof by contradiction. Suppose we want to prove that the statement P is true. Furthermore, suppose that we can find a contradiction Q such that no P implies Q is true. Because Q is false, but no P implies Q is true, we can conclude that no P is false, which means that P is true. How can we find a contradiction Q that might help us to prove that P is true in this way? It is actually quite easy, and it's one of the tricks that sometimes we have to use to make certain proofs. Again, as you can see in the truth table, For the conditional statement to be true when Q is false, then P has to be false. If we prove that no P implies Q is true, then when Q is false, then no P has to be false. If no P is false, then P is true, and we just prove our theorem. We already know that R and no R is a contradiction whenever R is a proposition. We studied that before in the previous videos. Now, we can prove that P is true if we can show that no P implies R and no R is true for some proposition R. Proof of this type are called proofs by contradiction. Because a proof by contradiction does not prove a result directly, it is another type of indirect proof. Let's see the following example. Show that at least 4 of any 22 days must fall on the same day of the week. Let P be the proposition at least 4 of 22 chosen days fall on the same day of the week. If we choose, you're supposed to prove now that no P is true. This means that at most 3 of the 22 days fall on the same way of the week. If we choose at most 3 days and a week has 7 days, at most 21 days could have been chosen. At most 3 of the chosen days could fall on that day. This contradicts the premise that we have 22 days under consideration. We just saw before that now we only can have at maximum 21 days under consideration. That is, if R is the statement that 22 days are chosen, then we have shown that no P implies R and no R, which is a contradiction. Consequently, we know that P is true. We just proved that at least 4 of 22 chosen days fall on the same day of the week. Again, as you can see, the last step of the proof is to recap the theorem. Never forget to do that. Let's see another example. Prove that square root of 2 is irrational by giving a proof by contradiction. So let's P be the proposition square root of 2 is irrational. To start a proof by contradiction, we suppose that no P is true. Then no P is, it is not the case that square root of 2 is irrational, or no P is equal to square root of 2 is rational. Let's now show that assuming that no P is true leads to a contradiction. If square root of 2 is rational, there exist integers a and b with square root of 2 equal to a divided by b, where b is different than 0 and a and b have no common factors. So that means that the fraction a divided by b is in its lowest terms. You cannot make it a and b any smaller number. Because square root of 2 is equal to a divided by b, when both sides of this equation are squared, it follows that 2 is equal to a squared divided by b squared. Hence, 2b squared is equal to a squared. Here we are just transforming the equation. We didn't do anything else. By definition of an even integer, it follows that a squared is even. We proved that before. So next, we use that the fact that a squared is even, a must also be even. If a is even, then a is equal to 2c for some integer c. Thus, 2b squared equal to a squared, we can transform that in 2b squared equal to 4c squared. Dividing both sides of this equation by 2 it gives us as a result that b squared is equal to 2 times c squared. By definition of even, this means that b squared is even. Again, using the fact that if the square of an integer is even, then the integer itself must be even. We conclude that b must be even as well. So, what we have now shown that the assumption of no p leads to the equation square root of 2 equal to a divided by b, where a and b have no common factors, but both a and b are even. That is, 2 divides both a and b. Okay? So, the statement square root of 2 equals to a divided by b, where a and b have no common factors, means that in particular 2 does not divide both a and b. Because our assumption of no p leads to the contradiction that 2 divides both a and b, and 2 does not divide both a and b, no p must be false. That is, the statement p square root of 2 is irrational is true. We have proved, therefore, that square root of 2 is irrational. To prove a theorem that is a biconditional statement, that is, a statement of the form p if and only if q, we show that p implies q and q implies p are both true. The validity of this approach is based on the tautology p if and only if q, if and only if p implies q and q implies p. We already stated before that to show that statement of the form for all x p at x is false, we need only to find a counterexample. When presented with statement of the form for all x p at x, which we believe to be false or which has resisted all proof attempts, then we look for a counterexample. Many times in mathematics, counterexamples are used to prove that certain statement is false. So this will be another technique that we will have in our arsenal when we are working with proofs. Let's see an example. Show that the statement every positive integer is the sum of the square of two integers is false. We look for a particular integer that is not the sum of the squares of two integers. 3 cannot be written as the sum of the square of two integers. To show that, note that only perfect squares not exceeding 3 are 0 and 1. Furthermore, there is no way that to get 3 as the sum of the two terms each of which is 0 or 1. Consequently, we have shown that every positive integer is the sum of the square of two integers is false using a counterexample. Now, let's see some mistakes that sometimes we can make when we are creating proofs. The most common errors are mistakes in arithmetic and basic algebra. Even professional mathematicians make such errors, especially when working with complicated formula. Whenever you use such computations, you should check them as careful as possible. Each step of a mathematical proof needs to be correct, and the conclusion needs to follow logically from the steps that precede it. Many mistakes result from the introduction of steps that do not logically follow from those that precede it. Let's see this example. This is kind of a popular proof that you can find outside there, that it is a proof that 2 equals 1. So let's see the steps. The premise of the theorem is a and b are two equal positive integers. And from there, someone is trying to draw the conclusion that 2 is equal to 1. So the first step, A equals B, is given, is the premise. Now if we multiply both sides by A, we get A squared equal to AB. If we subtract B squared from both sides, then we get step 3, A squared minus B squared equal to AB minus B squared. If we factor both sides, then we get A minus B times A plus B equal to B that multiplies A minus B. If we divide both sides of equation 4 by A minus B, then we get 2B is equal, then we get A plus B equal to B. After that, if we replace A by B, remember that A is equal to B, and simplify, we have that 2B equal to B. If we divide both sides by B, then we just apparently prove that 2 is equal to 1. So everything looks good. Where is the mistake here? The mistake is simple. The mistake, we find it in step 5, when we divide both sides by A minus B. We cannot do that because A minus B is 0, because A and B are equal. And as you must know, division by 0 is undefined. So you cannot divide by A minus B because A minus B is equal to 0 and division by 0 is undefined. Here you just have a common error in this case for not to follow the rules of arithmetic. So you must be careful when you do proofs to not make a mistake on arithmetic or algebra. Let's see another example. Is the following argument correct? It supposedly shows that n is an even integer whenever n squared is an even integer. Suppose that n squared is even, then n squared is equal to 2k for some integer k. That's the definition. Now the next step, say let n equal to 2l for some integer l. This shows that n is even. So the argument is incorrect. We didn't give any argument to show that n can be written as 2 times l for some integer l. As you can see, we are just assuming that n is equal to 2l. This is circular reasoning because we are assuming a statement that is equivalent to the statement being proved. In another way, you cannot assume a statement that is the same that you want to prove, okay? Otherwise, the proof will never be right. Of course, the result itself is correct. N is an even integer whenever n squared is an even integer. What happened here is that the proof is the one that is wrong. Making mistakes in proofs is part of the learning process. When you make a mistake that someone else finds, you should carefully analyze where you went wrong and make sure that you do not make the same mistake again. Even professional mathematicians make mistakes in proofs. More than a few incorrect proofs of important results have fooled people for many years before subtle errors in them were found. So, don't be scared of making this type of mistakes. Remember, in this topic, as in the rest of the topics in mathematics, the more you practice, the better you will get at it. So, as a conclusion, we have now developed a basic arsenal of proof methods. What we should do is we try one method. If we don't get the expected result, then we move to the next method in our arsenal. We study different methods and strategies to create proofs. And there is an important takeaway that there is no procedure to write the proof of a theorem. You just use the general method and then you combine the axioms with rules and inference, with premises, on the best way you can. If you don't get the expected result, you try again using a different way. So that is all for this video. Thank you very much for watching. I will see you in the next video.